Continuing on with gases today, we'll be introducing some additional gas laws. Today's lesson is a little bit tricky, but I'm sure that you will do a great job with it as we focus. First up is Dalton's law of partial pressure. And Dalton's law of partial pressure states that if you have a mixture of gases, let's say, for example, that we had some type of bottle in which we had oxygen gas and helium gas and not yet. Neon gases. Guys, pass this for emergencies only today. We don't want kids wandering around. We need to be safe. The total pressure that these gases exert, and keep in mind that gases move in a straight line fashion, exerting pressure on the walls of the container. The only thing that will change its path is a collision with the walls of the container or with another gas molecule. So the total pressure is equal to the sum that all the partial pressures exert. So it's going to be the sum of the partial pressure of oxygen gas plus the partial pressure of helium gas plus the partial pressure of neon. And again, PT, total pressure. So the total pressure is equal to the sum of the partial pressures of all the gases in the container. It is a little bit tricky to collect a gas, because to collect a gas in a classroom or outside, there's air all around you, and air is a mixture of gases, and you don't want all of those gases mixed in with the gas you're trying to collect. So typically what you will do is you will collect a gas over water by putting it underwater. For example, let's say that we had a trough or some type of bucket that was filled with water, maybe not to the tippy top because that might make a mess. And this is what you'll be doing in your next lab. Let's say that we have a graduated cylinder, and this graduated cylinder is filled to the tippy top with water. We can cover this graduated cylinder with parafilm or saran wrap, and then we can invert it into the tub of water. And if you do a good job, you won't lose any water that is in there. And again, we have water in here as well. What we're going to be doing in the lab is you are going to have a lighter. Ooh. But no pyro tricks. You're going to have a lighter, and if you push down on the trigger, you will release the gas, which in this case is butane, into the graduated cylinder, and it will travel up the graduated cylinder and water will get displaced outward. And you will continue to do this until you've collected some volume of gas that the lab calls for. Let's say that we do this and we collect 50 mils of gas. And shown here in red will be the gas we collected. Does water have the ability to evaporate at any temperature? Sure it does. If you leave water out the next day, you'll have a little bit less. The higher the temperature, the greater the rate of evaporation. But nonetheless, some liquid water molecules will evaporate into the gaseous state. So in addition to the gas you collect, when you collect gas over water, because now the gas is on top of the water, why does the gas sit on top of the water? It is less dense. But you will have some water vapor in here. But that's the only gas that you will have collected in addition to the one you wanted to, whereas if you collected it in the air, you'd have a whole bunches of gases mixed in here. And now we can apply Dalton's law of partial pressure. Dalton's law of partial pressure says the sum of the partial pressures is equal to the total pressure. So keeping that in mind, the total pressure will be equal to the pressure of the gas you collected plus the pressure of the water vapor. Now the pressure of the water vapor is temperature dependent, and you saw that in the previous lab, although it probably didn't quite come together for you. So in the previous lab, you saw that at a given temperature, water vapor exerts some pressure on the walls of the container. For example, if the temperature is 20 degrees Celsius, the pressure was 2.34 kPa. If the temperature is 25 degrees Celsius, the pressure is 3.17 kPa. If it's somewhere in between, and it might have been in your lab, let's say the temperature was 22 degrees, that would just involve a little extrapolation. You would subtract 2.34 from 3.17. You would divide by 5, and that would give it to you for each degree. So you could easily figure it out, and we'll be exploring that in the lab a little bit more next week. So let's say, for example, actually I think I have an example built right into your notes. I do. So you can collect a gas over water using a technique known as water displacement, and this is exactly what you're going to be doing in the lab next week, where you will be determining the volume of gas, the pressure of gas, in an ultimate determination of R, the universal gas constant, and we'll talk about that next week. Water displacement, I wrote it all out here. But again, you will get some water vapor mixing with the gas that you're collecting, and you need to correct for that. So Dalton's law of partial pressure says the total pressure is equal to the sum of the partial pressures. And again, these are partial pressures of gas A, B, and C respectively. The first example looks wicked hard, and it is extremely easy. It says, what is the pressure of hydrogen gas collected over water at 24 degrees Celsius? The water levels inside and outside the collecting bottle are equal at the end of the experiment. And that I do want to explain. When you do these experiments, you need the water level outside and the water level inside to be the same. Once you have equalized for pressure, your total pressure here is equal to atmospheric pressure, which we get from a barometer we got off the internet the other day. So when you do your experiments, you want to equalize those, you want those water levels to be the same to equalize the pressure. If you can't, you have to make a correction for it, and you'll see that in your next lab. It says the atmospheric pressure is 94.4 kPa. At this temperature, that is 24 degrees Celsius, the vapor pressure of water is 3 kPa. Based on the vapor pressure of water and atmospheric pressure, which is total pressure, how do we get the pressure of the hydrogen gas we collected? So we've got an atmospheric pressure equal to 94.4 kPa. We've got a pressure of water vapor equal to 3 kPa. And we want to know the pressure of the gas we collected, in this case, hydrogen gas. How would we do that? Is atmospheric pressure equal to the total pressure? Yes, it is, because you equalize those two water levels. We know the total pressure is equal to the pressure of the hydrogen gas we collected plus the pressure of the water vapor. We have this and we have this. So the pressure of the hydrogen gas is equal to the total pressure minus the pressure of the water vapor. That's 94.4 kPa minus 3 kPa. Remember, when you subtract, you go to the least number of decimal places, is 91.4 kPa. So it looked really hard, but it's ridiculously easy. Total minus the water vapor pressure will equal the pressure of the gas. Very often, you will combine Dalton's law of partial pressure with the combined gas law that you were assessed on the previous quiz. And we are going to link these two formulas together in the next problem. It says some hydrogen gas is collected over water at 20 degrees Celsius, which corresponds to a water vapor pressure of 2.34 kPa. Atmospheric pressure is 115.5 kPa. The water levels inside and outside the collecting bottle are equal at the end of the experiment. The total volume of the sample was 2.93 liters. Calculate the volume of the hydrogen gas at 30 degrees Celsius at 1.59 atm. Let's take a look. A lot going on there. Let's read through it carefully so we can figure out all the pieces. And this is tricky on multiple levels. It says some hydrogen gas was collected at a temperature of 20 degrees Celsius. Again, this whole chapter is Kelvin. If you don't use Kelvin, you are going to crash and burn. That's the first temperature given. The water vapor pressure is equal to 2.34 kPa. Atmospheric pressure, that's going to be the total pressure because you equalize those water levels, is 115.5 kPa. And the total volume, that's V1, is 2.93 liters. So again, as I work these word problems out, I yank out key information so that I can try and figure out which formula is going to assist me in solving the problem. It says calculate the volume again. So here's the second set of conditions. The temperature is 303.15 Kelvin, and P2 is 1.59 atm. There's a lot going on here. Do we have P1? Not yet. How are we going to get P1? Well, that's going to be the total minus the water, right? Just like the previous problem. And on the quiz, I set that up for you so you don't forget to do it. 115.5 minus 2.34, and that is 113.2 kPa. So the first thing we do is we get the pressure of the hydrogen gas under the first set of conditions. Be very careful there. Now there's one more sticky point in this problem. And for those of you who write out quantities, you would catch it. But for those of you who tend to only write numbers, you could miss it. Once I have P1, I very often will scratch these out because I don't want to use those and I don't want to confuse myself. What's the other sticky point that you see? Right. You can see P2 is an ATM, so you've got different units of pressure and they've got to be the same or they won't cancel. So I gave you kPa, and I will provide you with those equalities, and you can do a simple conversion from kPa. 1 kPa is 1,000 pascals, and then 1 ATM, 2 pascals. You would be provided with this equality directly on your quiz if an equality is needed. 1 atmosphere is 101,325. And again, that cross cancellation of units. So you've got 113.2 EE3 divided by 101,325. And that's going to be 1.117 ATM. That is my P1 that I'm going to use. Make sure you note it in some way so that as we continue on, you use it. The second part of the problem is review stuff that we've done already. You now have P1, B1, and T1, and you want to solve for V2. P2 and T2 are given as well. Those of you stronger in math are very successful in these types of problems, and you'll see it when I return your quiz shortly. Some of you had terrible difficulty manipulating variables. If you ever have a situation where you have two temperatures in the same part of the fraction, you've made a mistake. Keep in mind, volume is divided by temperature. So in order to get that away from volume, it's divided by here. It needs to be multiplied here. P2 is multiplied to V2. In order to get rid of that, that's like a 3x situation where you want x, you divide over here. Most of you were really comfortable manipulating variables. A few of you need a little more practice and you'll get there as well. Once you have it set, there's nothing different here from what we did the other day. Make sure you use the correct P1. You did all that work to get it. And some of you are also having a little bit of difficulty with your calculators. Again, the only parentheses you need are the ones in red. If you have trouble doing that, you can multiply the denominator and flip it to the numerator. That's how I do it. I can show it to you if you are interested. And I get a V2 of 2.13 liters. And that type of problem is a little more involved. There's a lot going on. Make sure you get P1, check its unit, and then solve for V2. Questions on number 2?
Why did you cross those two?
I only crossed them out because I knew I didn't need them once I got the pressure of the gas by doing the total minus the water. I canceled them just because I didn't want it to confuse me. I knew once I got to here, that's what I needed to plug in for P1. And very often kids will get this and go back to this, so probably a good idea to scratch it. Questions there? Number 3 is very similar. Give it a shot. I'll reveal the answer in a few minutes. Try it. See if you can do it. Are you done? Are you done? I was just kidding. It was a joke. It wasn't funny. It was funny because you laughed. Were you able to get P1 in kPa? What was that? What'd you get for P1 in kPa? 117.3 kPa. What is the equivalent in atmospheres? 1.158 atm. All right, let's see if you got it. Yes, yes?
How do you get P1?
The way we get P1, see, this is what happens when you go PP, haha. Just kidding. The way you got P1 is you do PT, which is the total pressure which was given, minus the water vapor pressure which was also given. So 120.5 kPa minus 3.17 kPa. Once you get that, you have to convert to atmospheres because this was given in atmospheres. Once you do that conversion, make sure you plug that in here, and you get 260 mils. Yeah?
Where'd you get like the 101 PA like in the whole box?
That would be given. You would be given these conversions. Given. That's why I didn't assess on these conversions on the first quiz because I knew I would hit it on the second one. And your problem on the quiz is very similar to numbers 2 and 3. Very similar. I've got another concept I want to show you, but I do want to indicate that the classwork that goes with this type of problem is classwork 3.2a, which you already have 13 through 17. And those should be done for Monday to make sure you understand this concept. You're combining Dalton's law of partial pressure with the combined gas law. And again, if you work through those, you'll be golden. The quiz problem is grossly similar to number 2 or 3. In fact, it's broken down a little bit more, so it's a little bit easier than 2 or 3. You'll recognize to do it. All right, another concept we want to talk about today dealing with gases is effusion and diffusion. And diffusion, I would think that you saw a little bit of in honors bio. For example, if you had 2 cells connected by a semi-permeable membrane, and let's say you had some solute here and less of it here. Diffusion is the process by which particles move down their concentration gradient from high to low. And I would think in biology you learned about it a little bit with hypertonic or hypotonic solutions. Right, and you, exactly, perfume. If somebody sprayed stinky perfume in the back of the room, those of you sitting in the back, you would be like, ooh, right away. And I wouldn't smell it as fast until the particles diffused from a high area of concentration to a low one. Similarly, after lunch or maybe during lunch, somebody will probably cut one, and you will be like, oh, gosh. And everyone sitting in that immediate vicinity doesn't like it, and then soon people at other tables smell it too. So that would be another example of diffusion. And you can see both diffusion and effusion in action. You've learned a little bit about diffusion already. Effusion is the passage of a gas through a small opening. So let's say you went biking and you went over a nail, and all of a sudden your tire was flat. The air in your tire moved from the tire tube out through the opening. Graham's law shows that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. The greater the molar mass, the slower it moves. And you can think of it this way. if you ran a race against a 450-pound person, I would hope that you would win. So the greater the molar mass, it's going to be the slower you move. The smaller the molar mass, the faster you move. So inversely proportional to the square root. The math here is a little tricky. We'll move through it very carefully. Again, diffusion, movement of gases down concentration gradient. Effusion describes the passage of a gas through a tiny orifice or hole. The rate of effusion measures the speed at which the gas is transferred from one area to another. And you can see effusion in action here.
Fusion is the process of gaseous atoms flowing into a vacuum through a hole in a container. The rate of effusion of gas molecules at constant temperature and pressure is inversely proportional to the square root of the molar mass of the gas.
What's also kind of cool is you can see diffusion here.
Diffusion is a process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the two gases meet, a precipitation reaction occurs, forming ammonium chloride. The mass of the hydrogen chloride molecules relative to those of ammonia is greater. Thus, hydrogen chloride molecules travel more slowly. Diffusion
And
is
if you look at this right at the very end
molecules
here,
travel more.
you can see this white precipitate forming right here. Why is it closer to this end than this end?
The hydrogen chloride has a heavier molar mass.
Greater molar mass, for sure. This is going to be about 36.5, and this is about 17. So if they finish dead center, they would have the same molar mass. And if they finish closer to one than the other, then this has the greater molar mass. Good. All right, let's take a look at Graham's law right here. It says the velocity of gas A over the velocity of gas B is equal to the square root of the molar mass of gas B over the molar mass of gas A. And again, note the inverse relationship, hence the crisscross. And we'll use this formula. Now, some of the kids always say, well, what should be A and what should be B? Whatever you're solving for should go in the numerator. If you do that, you'll have a much greater likelihood of success. In the first example, it says neon effuses at a rate of 3 meters per second. At what rate does carbon monoxide gas effuse under the same set of conditions? So let's take a look here. The rate that neon effuses, or the velocity lowercase v of neon, is 3 meters per second. We want to know the velocity of carbon monoxide. You have to be able to formula right. The molar mass of neon off the periodic table is going to be 20.180 grams per mole. And the molar mass of carbon monoxide, you've got 12 and about 16, 28 point, probably a 10. When you use Graham's law, whatever you are solving for should go in the numerator. Whatever you are solving for should go in the numerator. I'm going to solve for the velocity of carbon monoxide. I'll put that over the velocity of neon is equal to the square root. Don't forget the crisscross. If carbon monoxide is here, it's on the bottom here. Neon here. So I want to get carbon monoxide's velocity on its own. So I'm going to move this here. And at this point, I'm ready to plug and chug. Much easier to move variables than quantities. The molar mass of neon is 20.180 grams per mole. The molar mass of carbon monoxide is 28.010 grams per mole. And I'm going to multiply that by 3 meters per second. And I always like to make sure that my answer makes sense. Which has the greater molar mass, carbon monoxide or neon? Not a trick question. Carbon monoxide or neon, greater molar mass? Carbon monoxide, this quantity is greater than that. If it has a greater molar mass, would you expect it to move slower or faster? Does it? Yes, it does. That's a good indication I've set it up properly. Let's flip the whole problem around and try and solve for molar mass. Before doing that, let me ask a question or two. Let's say that I run 3 times as fast as Gavin. Sorry. How could I set up a simple proportion? What should I set you at?
1/3.
If you wanted to avoid the fraction, how else could you do it?
43.
Okay. I'm not phrasing it properly. Let's say that I run 3 times as fast as you, and I run at a rate of 3 meters per second. What do you run at?
1 meter.
1 meter per second. So if you know one of them, and if you know somebody moves 3 times as fast as somebody else, set that person at 3 and set the other one at 1. Make it very simple. We could have made it more complicated because you could have said, okay, you run 3 times as fast as I do. I'm going to set you at 9, and you would set the other one then at 3, which is 1/3. So you can do it whichever way you want. Usually the kids find it easier to set something at 1 and then the other based on what's provided. It's usually easier when you're solving for molar mass. Let's take a look at that. Let's keep that in mind, taking a look at this problem. And this problem's written a little bit tricky. Yours will be much more straightforward. It says, what is the molar mass of a gas that diffuses at a rate that's 0.67 times that of oxygen gas? So it's slower than oxygen gas, which means it must be heavier. And then we want to identify the gas. Let's take a look. Let's get the information down and see what we can do. On number 2, we want to know the molar mass of some unknown gas. The velocity of the unknown, which I'm abbreviating UNK, is 0.67 times that of oxygen. I'm going to set that at 0.67 meters per second. I'll set set the velocity of oxygen gas at 1 meters per second. The 1 is not a significant digit. It's just what I set it toward. It is significant, but it's not going to be a significant digit toward our final answer. We want to know the molar mass of the unknown. The molar mass of oxygen gas, a diatomic element, is 31.998 grams per mole. And we also want to ID the gas at the end. So again, the unknown effuses at a rate that is 0.67 meters per second. So I set that one that way, and I set the other one at 1. Just keep it simple. Now again, whatever you're solving for should go in the numerator, and that's how I'm going to base my whole equation. The molar mass of the unknown over the molar mass of oxygen. I put the unknown in the numerator because I am looking for it. Make sure you crisscross now. Velocity of oxygen over the velocity of the unknown. How do you solve for something that's in a radical?
Power of
Square it.
No, it's not, Captain. Oh, yeah.
Square both sides. You get the velocity of oxygen gas over the velocity of the unknown is equal to the molar mass. The velocity squared is equal to the molar mass of the unknown over the molar mass of oxygen. So you square both sides, and then you want to solve for the molar mass of the unknown, so you'll multiply that by this. So again, we set up the equation, putting what we want to solve for in the numerator. We square both sides. That gets rid of the radical, and now we can solve. The molar mass of the unknown is equal to the molar mass of oxygen gas times the square of the velocity of oxygen gas over the velocity of the unknown. Don't forget to square that. That's the common mistake kids make. What did you say?
I said, we're not kids, we're teens.
Oh, I tried to make it super big, but I think it got too big. And I get a molar mass of 71 grams per mole. Now, we have to figure out what gas that is. Let's look on the periodic table. 71 falls within these two. Is gallium a gas? No. Is germanium a gas? No. Uh-oh. What are you thinking?
It's fake.
It's not fake, silly.
All of them be gases?
No.
Oh, never mind.
No, silly.
You just heat it up.
We have a molar mass of 71 grams per mole. There are 5 diatomic gases. What gas is this?
The one that's 30 something. 30.
Half of 71 is 35 and a half. And it's chlorine gas, right? So if you get a molar mass that doesn't match a gas on the periodic table, divide it by 2 and you will find your winner.
That's tricky. I'm gonna do that.
chlorine gas. This is Graham's law of effusion. Little tricky on the math here. I've got an additional problem for you to try, which I will put on the screen, and you should try that one. I do want to mention...
Just one brief announcement before Vista Venom strikes today. Just a friendly reminder, students, First Priority Club will be meeting today in room 10104. Please join us for an inspirational word, fellowship with your friends, and we will see you there. Once again, it's 10104. We have two Cobra Kudos going out today. We have one from Mrs. Catton to Amanda Dennett. Amanda found a wallet and turned it into student services. Way to go, Amanda. We have another one from Miss Dalkansky, Maria Ortiz. She found a cell phone and turned it into Miss Dalkansky. Way to go. Way to go, girls. At this time, teachers, please turn on your computers and prepare for this afternoon's video announcement. This event strikes now.
All right, last thing I want to mention, again, if you get a molar mass that doesn't match a gas on the periodic table, think about dividing it by 2 to get a diatomic element. In your notes, you should try and do number 3. I'll reveal the answer in a minute or two. And in your classwork for Monday, you want to do these problems as well. We will continue on Monday, and I will give you some practice time as well. And then we will work on the lab next week. So don't worry about it. We'll have more than enough time to do it. Try and do number 3 before you walk out. We still have several minutes. I will show the answer so you can do a quick peek once you get it. But don't peek till you do it. All right, so hopefully in regard to Graham's law of effusion, you're comfortable with those calculations, and then also Dalton's law of partial pressure. The 2 that I did with you are probably the trickiest in terms of what you will see on the next quiz. So some extra practice will serve you well.